Welcome back. As promised, in this video we will be discussing related rates problems. There is no new theory in this section, but the style of problems we'll be discussing is something we haven't encountered before. So I will just jump right in and start with an example. A 13-foot ladder leans against a wall. Suppose that its bottom slides away from the wall at a constant rate of 1/10 of a foot per second. How fast is the ladder's top sliding down the wall at the moment when it is 1 foot above the ground? Well, as I advised you when we were doing optimization problems, the first thing you need to do is just screw around with the problem a bit. Make sure you understand exactly what it is asking. Be sure you understand why it is a legitimate problem in the first place. And only after getting a feel for it should you then start writing down symbols and so on and so forth. This is a very typical sort of related rates problem. You will find some variant of it in any textbook. This is, in fact, the first example in the section in my book, and no one ever gets out of a calculus class without solving various problems about ladders leaning against walls, especially unstable ladders that slip away from the wall. Be that as it may, let us commence to screwing around. Whenever we can draw a picture, we should, and this particular example cries out for one. Something like this. We have a wall and the ground and a ladder leaning against the wall. We're told that the ladder is 13 feet long. Let's go ahead and label that. And we're also told something about the bottom of the ladder, this point right here. We're told that it's sliding away from the wall, it's sliding out like this, and it's sliding out at a constant rate, namely at 1/10 of a foot every second. So I'll remind myself of that by writing down here 1/10 of a foot per second. And the idea in this problem is that as the bottom slides away from the wall, the top remains in contact with the wall. So by pushing the bottom away, the top comes down. Okay, these first two sentences are already making more sense. Let's move on. We are asked how fast is the top, this point right here, sliding down the wall at some particular moment. And before we get to that moment, we might ask, well, why do we even need to specify a moment? If the bottom is moving at a constant rate, shouldn't the top be moving at a constant rate too? Is there something I'm missing here? Well, it turns out that if the bottom moves at a constant rate, the top does not move at a constant rate. You can see this by messing around with it a bit, especially if you try to draw some reasonably accurate pictures. But I've cooked up a little demonstration on GeoGebra that will work better than my pictures, so I will bring that up right now. Okay, this blue line represents our ladder, and we have the bottom labeled as such and the top labeled as such. And the ladder is 13 units long, and I can slide it around on the bottom, and the top moves accordingly. And what I wished to show you with this demonstration was that even if the bottom is moving at a constant rate, the top does not fall at a constant rate. For example, here the bottom is at 5. Let's imagine that in one tick of the clock, it moves 1 unit over. So it's going to move from 5 to 6. And when it moves from 5 to 6, what happens to the top? Well, the top was at 12, and at 6, one tick of the clock later, it's down to something like 11.5. So at that moment, it seems to be moving roughly half a unit downwards. The top is moving half a unit downwards per second. But sometime later, if the bottom continues to move 1 unit per second, let's just say, and it's down, say, at 11, when the bottom is at 11, the top is at around 7. Well, 1 second later, one tick of the clock later, when the bottom moves to 12, the top is down to 5. So when the bottom moves 1 unit to the right in 1 second, or whatever our unit of time here is, the top falls 2 full units down from 7 to 5. Very different from when we were looking over here. And of course, the more extreme we go, the more pronounced the difference is. When we go from 2 to 3 on the bottom, the top barely moves from just under 13 to still very close to 13. When we move from 11 to 12, we go from 7 all the way down to 5. Of course, as the bottom approaches 13, it's going to fall all the way down because the whole ladder is 13 units long. So as we move in that final unit, it moves really fast to the bottom. Bang, it hits there. Okay, so as you can see, the constant speed on the bottom does not translate to constant speed on the top. Let's get back to the blackboard. All right, here we are again. Now let's get back to this last sentence, which is what led us to GeoGebra. I asked, how fast is the ladder's top sliding down the wall at a particular moment? Namely, when it, the ladder's top, is 1 foot above the ground. So when it's very close to the ground. Well, as we saw in our little computer demonstration, we should imagine it's falling pretty fast, at least relative to other positions. And you might say at this moment, oh, wait a second, my preliminary drawing's all wrong. It should look something more like this because there's only 1 foot here. Well, not so fast. Save that thought and we will come back and redraw this later. But for now, I do not want to draw my initial drawing with this specific moment in mind when it's 1 foot above the ground. Well, why not? Why don't I want this thing to be 1? It's because we are discussing how two things are changing. This distance right here and this distance right here. And if I want things to be changing, which I desperately need if I want to do calculus, if I want things to be changing, I do not want to freeze my picture too soon. I don't want to lock it in to this one particular moment where that height is 1. I want to leave, as I describe it in the book, some slack in the system so that I can move things around like on that GeoGebra picture. Because if there's no possibility of motion, there's no possibility of change, and therefore we can't do differential calculus, which is all about change. So I'm going to leave this as is, and only at the very end of the problem will I specify this particular moment when the top is only 1 foot above the ground. For now, I want to leave these as variables so that they can change. Let me go ahead and give them names. I will let x be the distance of the ladder's bottom from the wall, and y be the distance of the ladder's top from the ground. And we're interested in this problem in how y changes as a result of changes to x. We already know how x changes. This point is moving to the right at 1 foot per second, so x is getting bigger at a rate of 1 foot per second. And just by messing around, we understand that y is changing at different rates at different times. And we are trying to relate these two rates to one another. This is why it is a related rates problem. Well, I find that to solve any related rates problem, a very good approach, once we have a picture, if such a thing is appropriate, and we have obtained a good idea of what the problem is all about, is to write down what we know about any of the rates involved and what we want to know about any other rates that are involved. So here, for example, we know something about the rate at which x changes. And as I'm writing down what we know and what we want to put everything in the symbolism of calculus. Well, we know that since this point is moving at 1/10 of a foot per second, x is increasing at 1/10 of a foot per second. And if I want to say that x is increasing, how do I put that in terms of calculus? Well, it's a rate at which x is changing in time. Every second, it is increasing by 1/10 of a foot. So the rate of change of x with respect to time, that is dx dt, we know is going to be 1/10. Be sure you understand this. It's a translation, essentially, of this sentence right here, given the meaning of x. The rate at which x changes with respect to time is 1/10 of a foot per second. We'll put the units there. Okay, so far so good, but I also want to write down what it is that we actually want as far as our related rates are concerned. We know how x is changing in time. We want to know how fast is the top sliding down the wall at a particular moment. Well, the distance of the top from the ground is given by y. So the speed at which that top is falling is, of course, the rate at which y, that distance, is changing. So what we want to know is dy dt at a particular moment. And we have to specify that moment because we know it differs at different times. So we want to know what is dy dt. How is this length right there changing in time when the ladder's top is 1 foot above the ground? Well, that means when y is equal to 1. And I guess I should say 1 foot to be precise. Okay, we are halfway there now. We understand what's going on. We've got a picture of the general situation. We've translated what we know and what we want into the language of calculus, and using these symbols, x and y, that we've introduced. And now the question is, how do we get to this from this? Well, we ultimately want an equation relating these two rates. That's why these are related rates problems. Once I have an equation relating these two rates, well, then I'll be able to translate from one to the other. So our big question is, how do I actually relate these two rates? How do I relate the rate of change of x with respect to time and the rate of change of y with respect to time? Every related rates problem comes down to some question like this. How do I relate the two rates that are involved here? And the answer, in broad outline, is the same every time. To relate the rate of change of x and the rate of change of y, in other words, to relate the derivative of x and the derivative of y, what I have to do is relate x and y themselves without any reference to the derivatives. If I can do that, if I can come up with an equation relating plain old x and y, then it will be easy to translate that into a relationship between the two derivatives, because all I have to do is take derivatives of both sides with respect to t. So let's see this all in action. How am I going to relate x and y? Well, in this case, the answer is staring us in the face, provided, of course, that you drew a picture, because the ghost of Pythagoras calls to you and says, the square of x plus the square of y is the square of 13, which is 169. So let's go ahead and write that down. By the Pythagorean theorem, x squared plus y squared is 169. This equation is my relationship between x and y, the two variables involved in this problem, the two things that are changing. But as we've said, it's not just the variables that we want to relate, it's their derivatives. We're only using this relationship between the variables to get at a relationship between their derivatives. So how do I turn a relationship between x and y into a relationship between derivative of x with respect to t and derivative of y with respect to t? Well, of course, I'm going to take derivatives of both sides of this equation with respect to t. So, differentiating both sides implicitly with respect to t, it's implicit differentiation because I don't have x and y as functions of t, we obtain, first I'll just write it purely symbolically, the derivative with respect to t of the left-hand side is the derivative with respect to t of the right-hand side. Now I'm differentiating implicitly with respect to t. That means I am bearing in mind that x is a function of time and y is a function of time. I don't need to write down those functions explicitly, and it doesn't matter if I even can. I just recognize that x changes in time and y changes in time. Anyway, let's actually take these derivatives. The right-hand side is trivial, so I'll save that for last. But let's look at the left-hand side. Derivative with respect to time of x squared plus y squared. Well, remember, we are taking derivative with respect to time, not with respect to x or respect to y. We're thinking of x as a function of time. That means when I take the derivative of this first term, I actually have a chain rule problem here, because I have two functions. An inner function, x, which I've put in red just as a reminder that x is some function of time. And then the outer function is the squaring function. And while I'm at it, I'll go ahead and turn y red as well, because it too is some function of time. Obviously, you don't have to change them into different colors, but if it helps, go ahead and do it. So, back to our first term. Derivative with respect to time of x squared. Well, I need the chain rule, and the outermost function is the squaring function. We know the derivative of the squaring function is the doubling function, 2 times whatever, 2u. So that'll be 2 times whatever this is, but what goes there is the inner function itself, x. So I will pop x in here. But I'm not done because I'm doing the chain rule. I've taken the derivative of the outer function, evaluated at the inner function, but I still need to take the derivative of the inner function. And x is some function of t, so the derivative of x with respect to t is just dx dt. Good. And the same thing happens when we move on to the next term. When we take the derivative with respect to t of y squared, we need the chain rule once again because I have an inner function y, which is some implicit function of t, and the outer function, the squaring function. So derivative of the outer is 2 times whatever, but the whatever is the inner function, which is y, and I am not done. I have to multiply by the derivative of the inner function with respect to t, and that, of course, is dy dt, and I'm done with the left-hand side. As for the right-hand side, 169 is a constant. How does a constant change in time? Well, it doesn't change. It's constant. That means the rate of change is 0. Okay, let's take stock of where we are. We had our picture of the general situation right here, with its two variables, x and y, both of which implicitly are functions of time. They both change as time passes. And we found a relationship between x and y. With no mention of time, this holds at all moments, no matter what situation the latter is in. And then by taking derivatives of both sides with respect to time, we obtained this new relationship, which also holds at all moments. We haven't specified anything. We haven't frozen any one moment in time. So no matter what the ladder's position is, not only does this relationship hold, this relationship between x and y, but this relationship holds as well. This is a more complicated relationship because it links 4 quantities. X, the distance of the bottom of the ladder from the wall, y, the distance of the top of the ladder from the floor, dx dt, the rate at which the bottom is moving, and dy dt, the rate at which the top is falling. And what we have shown is that this relationship holds for all positions of the ladder. So at any particular moment, if I know any 3 of these 4 quantities, I should be able to solve for the 4th. And we're looking for one of them, dy dt, at a particular moment. So now, at long last, is the time when we want to specify, okay, this holds for all positions of the ladder. What does it tell us in this very particular moment? So, in particular, it holds when y equals 1, the situation we want to know about. At that particular moment, the picture looks like this. We have our wall and the floor. The ladder is 13 feet long, and its top is just 1 foot from the floor. Since I know 2 sides of the right triangle, I can get the third by the Pythagorean theorem. That will be, let's see, the square root of 13 squared minus 1 squared. That's the square root of 168. So at that moment, the picture looks like this, and our equation, this one, to refer to it, I'll give it a name. Let's call it star. So our equation star becomes, well, let's see. On the left-hand side, we have the first term, 2 times x. Well, at this particular moment, x is the square root of 168. So we're going to have 2 root 168 times dx dt. But we know that dx dt is 1 over 10 for all positions of the ladder, including this one. Let's move on to the second term, where we have 2y. Well, that's going to be 2 times the value of y in this particular moment, which is 1, times dy dt at that moment. Well, what's the value of dy dt at that moment? I have no idea, but I will soon. And now bring down the right-hand side. So everything that's taking place here is the situation at this particular moment, the moment specified in this figure, the moment when y is equal to 1. And we've discovered that at this moment, this relationship holds. And there's only one unknown in this relationship, dy dt, so I can just solve for it. Since I'm running out of room here on the screen, I'm just going to alter my equation here. Please don't do that on tests, because I can't rewind your tests. I can only see what you've written down in the final product. Anyway, what's the first thing I would do to simplify this thing? Let's divide both sides by 2. Nothing changes on the right-hand side when we divide 0 by 2, but on the left-hand side, those 2 2's will disappear. And of course, this 1 isn't doing anything, so I might as well get rid of it as well. Now I'm solving for dy dt, so I'll leave that on this side of the equation, and I'll subtract this from both sides, which leaves me with this. Aha! Dy dt is this stuff. We could actually simplify this a little bit, because 168 is divisible by 4. It is 4 times 42, and everybody knows that the square root of a product is the product of the square roots. And I did all of this because the square root of 4 is, of course, 2, so I can cancel a factor of 2 from top and bottom, leaving me with minus the square root of 42 over 5. Now, let's interpret this to make sure it makes sense. The first question to ask is, does it make sense for this thing to be negative? Well, it's a rate of change. It's the rate at which y is changing in time. So this would be telling me that at this particular moment, y is decreasing its value. Does that make sense? Well, of course it does. Y is always decreasing its value at all moments, because since the bottom of the ladder is going this way, the top is falling, which means y is decreasing at all moments, and in particular at this moment. So the negative should not put us off. This is in fact telling us that at this moment, y is decreasing this many feet per second. So I should include those units here, that many feet per second. That is, to sum everything up in a sentence, when the ladder's top is 1 foot above the ground, at this particular moment, the ladder's top is sliding down the wall at a rate of root 42 over 5 feet per second. If you run that through a calculator, you'll find it's about 1.3 feet per second. And that is that. As you solve other related rates problems, you'll see the same basic pattern being played out over and over and over again. A strange-looking problem which takes a little while to decode, which you can often do by drawing a picture, introducing symbols where you need it, and then take the time to write down what you know and what you want about the two rates of change that are involved in the problem. Once you've got that far, you're halfway through. In any related rates problem, you're looking to relate two derivatives of two variables with respect to another, which is often time. How do you relate those two derivatives? Well, you relate the two variables whose derivatives they are. Sometimes that will be a fairly easy task, as it was in here, where it was just staring you in the face geometrically. Sometimes you have to think a little more about what's going on geometrically. I'll show you another example like that in a moment. Sometimes it might be provided by a relationship in physics or economics or whatever the context might be if you're working in those fields. But anyway, once you've related the variables themselves somehow in some equation, you're always going to take derivatives of both sides implicitly with respect to whatever variable is appropriate, typically time. That gives you some new relationship which will involve the variables and their derivatives. And it will hold for all situations that the problem covers, all possible values of the variables involved. Then and only after you have that relationship amongst the variables and their derivatives, only then should you specify to the specific moment in which you are interested. Once you do that, you just figure out what some of the pieces are in that relationship, plug them in, and then you should just be able to solve for the thing you want. That is the idea in a nutshell. Okay, as you can see, these related rates problems take a lot of time, so I'm just going to do one more here. I will clear out all this stuff. Like magic, it is gone, and we will start our second example. A conical tank, 12 feet deep, has a 14-foot diameter at its top. Water is constantly flowing into the tank at a rate of 30 cubic feet per minute. And at the same time, out of the tank at a rate of 20 cubic feet per minute. And the question we must answer is this: how fast is the surface of the water rising when it is 6 feet deep at that particular moment? There is our problem. We see it is a related rates problem because we are given information about the rate of water flowing in, the rate of water flowing out, and we're asked about the rate at which the water level is rising. And we will solve this using the same kind of ideas with which we solved the previous problem. First, we will just screw around with it, draw some pictures, get a feel for what's going on. So let's start with this conical tank. What would it look like? It's 12 feet deep and it has a 14-foot diameter at the top. So it would have to look something like this. Here's the 14-foot diameter and here's the 12-foot depth. Now, we're also told that water is constantly flowing into this tank, presumably from the top, and it's constantly flowing out of the tank, presumably from the bottom. Perhaps we have water flowing into a pipe that leads to the tank at 30 cubic feet per minute, and at the same time, we can imagine a pipe at the bottom through which water flows out at 20 cubic feet per minute. So this is a constant inflow of volume and a constant outflow of volume. Well, this situation can only last for so long, because if every minute 30 cubic feet are flowing in, while only 20 cubic feet are flowing out, then there's a net gain of 20 cubic feet of water in the tank itself every minute. The tank has only a finite volume, so eventually something will have to give. Perhaps the tank will burst, or the pipes will burst, or who knows what. But I don't really care about that part. We're only interested in this problem about what's happening at a particular moment when the depth of the water in the tank is 6 feet deep. It can go up to 12 feet deep, so we would be interested at the moment when it is 6 feet deep. And we want to know, at that particular moment, how fast is the surface of the water rising? In other words, how fast is the depth of the water in the tank rising? So let's think about the variables at play here. We're interested in the speed at which the surface of the water is rising. Well, the surface of the water at any moment looks something like this, and the rate at which it rises, as I said a moment ago, is the rate at which the depth is changing. So let's go ahead and introduce a symbol for that depth. I don't want to use d because d obviously shows up in other places in calculus. So let's use h for the height of the water. So ultimately we will be looking for something about how the height is changing, something about dh dt, how it is changing in time. I told you earlier that in any related rates problem, it helps to write down what we know and what we want about the various rates involved in the problem. So let's do that. What do we know? What do we want? Well, we just said that what we want is dh dt, the rate at which this height is changing. But this height changes at a different rate at different times. We specifically want it when it is 6 feet deep. So we want dh dt when h is 6. And all distances are being measured in feet here. So I'll note that there. Oh, and by the way, you should take a moment and convince yourself that dh dt, the derivative of height with respect to time, is not constant, which is why we have to specify a particular moment here. The rate at which height changes as time passes is going to be greater at the beginning when the tank is empty than it will be at the end when the tank is nearly full. But anyway, I will leave it to you to think that through. It all has to do with the widening of the tank as we go up, which means that the higher up we are, the longer it takes to increase the depth of the water. But anyway, we have stated what we want in terms of the symbols in this problem. Let's state what we know about the rates of change given to us. Well, that is all contained in this information right here, that the water is flowing in at a constant rate of 30 cubic feet per minute and out at a constant rate of 20 cubic feet per minute. Or as we've said before, that the volume of the water in the tank is increasing at a constant rate of 10 cubic feet per minute. That one fact is what we need. But to put it in symbols, I'm going to need another symbol on my figure. Let's let V be the volume of water in the tank. Obviously, V is some function of time. It changes as time passes, just as H itself is a function of time. That's why we can talk about dH dt, and why we can also talk about dV dt, which is something we know about. We know that this volume is increasing at a rate of 10 cubic feet per minute. And we're now halfway there. We have a rate of change we know about and a rate of change we want to learn about. To learn about this one, we will relate it to what we know already. Well, how are we going to relate those two rates of change? Exactly as I said we always do. The way to relate V's derivative and H's derivative is to relate V and H themselves. Once we have a relationship between V and H, then we can take derivatives, and it will give us the relationship between the rates. And you might want to pause the video here for a few minutes and see if you can work out a relationship between V and H on your own. And if you can, great. See if you can solve the whole problem. And if you struggle with it, that's okay too. You will get more out of the solution I'll give in a second if you have worked on it on your own first. Okay, did you do it? I hope so. Let's see. How are we going to get this relationship between the variables V and H? Well, they both relate to this cone of water inside our tank. V gives its volume and H gives its height. So this should work with some fairly simple geometry. Do we know ways in which the volume of a cone is related to its height? Well, sure. What do we know about a cone's volume? The famous result, which you should certainly know by now, an old one, it goes back to Democritus, is that if we have any cone, then the volume of the cone is exactly 1/3 of the volume of the cylinder that it sits in. It is a remarkable relationship. The volume of the cone is 1/3 the volume of the cylinder. That famous result is enough to get us started. From basic geometry, we know that V, the volume of the cone, is 1/3 of the cylinder in which it sits, which I've put here in green. Well, how do I find the volume of a cylinder? That's easy. That's obviously the area of its base times its height. So, what is the area of the base here? Well, the base is a circle, so its area is pi times the square of its radius. I don't have a symbol yet for the radius, so I had better introduce one. Let me draw that on my figure. R is the radius of the base of our watery cone. So with that in place, we've got the volume of the watery cone is 1/3 the volume of the cylinder in which it sits, and the volume of the cylinder is its base, which is pi times r squared, times its height, which is obviously h. Good. and I don't actually need those parentheses. Now at this point, we have made some progress. We have a relationship that involves v and h. So you might want to say, I know what to do. Take derivatives with respect to time. There's a problem though. Our relationship here relates three quantities. There's v and h all right, but we also have r in there. So before we take derivatives, we would like to eliminate this r, rewrite it in terms of h or v or both, but get it so that only the two variables that appear here are in our relationship. Okay, so how do we get rid of r? This is something we didn't have to worry about in the previous problem, but we do here. An extra complication. Well, I'd like to write r in terms of other variables. Let's look at our figure. There clearly is a nice tight relationship between r and h. Maybe we can work on that a little bit. And in fact, in all positions of the water, even if it's just a little cone like that, or the whole thing, r and h have to bear a particular relationship to one another, which is determined by the shape of the cone itself. Ah, this looks like a job for similar triangles. And after staring at this thing for a little while, you hopefully see what I mean. This right triangle right here, which has r and h as its legs, is obviously similar to this right triangle, which I've drawn in red. And while the blue triangle changes its size, though always preserving its shape, the red triangle is endemic to the tank. It does not change its size at all. This side is always 12, and this side is the radius of the cone's base, the tank's base. And since the tank's diameter is 14, this must be 7. So by similar triangles, the ratio of r to h, this thing to this thing, is always equal to the ratio 7 to 12, this thing to this thing. Or equivalently, if we clear the fractions over here, r is always going to be 7/12 of h, no matter how great or small the cone of water is. And this is terrific because it will allow us to eliminate r over here. We can just replace this r by this stuff. So substituting this into our volume equation yields that v is 1/3 pi, and then instead of r, we get 7/12 h squared times h. And if you multiply this out and simplify this, that becomes 49 over 432 pi h cubed. And of course, we're not surprised to get this cubic factor in here since we are talking about a volume. And now this relationship right here is the sort of thing we were looking for. It's a relationship between the variable v and the variable h, and there are no other variables at play. And note again that this holds for all situations here, whether we have just a little water in the tank or a lot of water in the tank. We have not specified yet the moment when it is 6 feet deep. As I said in the previous problem, we don't want to freeze the situation too soon. We have to allow for change if we are going to take derivatives, which of course we are going to do now that I have my relationship between v and h, which holds at all moments. So implicitly differentiating both sides with respect to t, because remember both volume and height themselves are variables dependent on how much time has passed, we obtain this. The derivative with respect to t of the left-hand side is equal to the derivative with respect to t of the right-hand side. And now let's carry out the computation. On the left-hand side, of course, we just get dv dt. But what about the right-hand side? The thing to remember is that h is itself a function of time. So this isn't just a function of h, it's a function of h which itself is a function of time. It's a composition of functions. We have an inner function, h, which is some function of time, and an outer function which cubes the result of that function and then multiplies by this constant. So to take the derivative of this composite function, we of course need the chain rule. So derivative of the outer function, that's going to give us 3 times this constant stuff times h squared. That's just the power rule, but we are not done. To use the chain rule, I have to multiply by the derivative of the inner function, which will give me dh dt. Good, and I can clean this up a little bit if I notice that 432 is divisible by 3. So knocking out a factor of 3 from top and bottom turns this constant into 49 over 144. And let's pause to reflect on what this means. We have just found a relationship, not like this one that related v and h, but a more involved one that involves h, v is actually nowhere to be seen, and the derivatives of v and h. So it relates three quantities, and it holds for any situation we might see here. So now that we have this relationship, now and only now is the time to freeze the picture, to specify what's happening at the precise moment when the water is 6 feet deep. Thus, in particular, when h is 6, dv dt is this constant times 6 squared as opposed to h squared, dh dt. But in fact, we know what dv dt is. At all times, dv dt is 10, so I can replace that with a 10. And now I have a relationship involving only one unknown, dh dt, at this particular time. So I can just solve for it. I'm going to move everything up so I have a little more room. That's better. So rewriting this, by solving for this, we can say that equivalently, dh dt is 40 over 49 pi. That's just basic arithmetic. And the units here, since we're looking at change in height over time, is feet per minute. And finally, I will summarize the result in a sentence. That is, at the moment when the water is 6 feet deep, the water's surface is rising at a rate of 40 over 49 pi, which is about 0.26 feet per second. And we are done. Well, that is the idea. As you can see, this related rates problem followed the same basic pattern as the other one. We had to think about the rate we knew, we had to think about a rate we wanted. The game was to connect those two rates in an equation, which we ultimately did down here. But the way we got to that equation was by relating the variables themselves independent of any derivative, which is what we did over here. That required us to think about a little geometry, and we only reached that, actually, by starting with an earlier version, which related the two variables, but had an extra one as well. So we had to eliminate that using a bit more of geometry, just some similar triangles. Each individual step should be fairly easy. The trick is just putting them all together into a coherent argument. And it is important that you provide an actual argument and not just a bunch of scratch work on a page. One should be able to look at your work and follow it. As you see, there are words here in English. Not many of them, but enough to show what's going on. You need to provide such an argument in your own work. And the further you go in mathematics, the more important this becomes. So do take care when you write up your work. Okay, these problems are so long that I'm going to stop with just two of them, and I will throw you into the deep end of the problem set. So work on those. Don't get too frustrated if you have troubles with some of them, and we will move on from there. This is the last section in Chapter 3, so we will soon be moving on to the very short Chapter Pi, which is all about limits. Until then, goodbye.